Good afternoon, dear student, and welcome to this 30th edition of our Numerical Method 2 class. So far, what we have done, we have looked at the trapezoidal rule. And recently, we covered the recursive trapezoidal rule, which was helpful to construct a more accurate approximation of a definite integral using a technique called Richardson extrapolation technique. And it is part of what we call Romberg technique. So we have covered all that, and I asked you to convert the MATLAB code that is in the note into Python. So I hope you did it. So today we will proceed with the Gaussian quadrature formula or quadrature rule. If you recall what we said that a quadrature rule is a formula, a rule that approximates a definite integral as a finite sum of the function evaluated at a certain point, the node point, times a certain weight. So it's a linear combination of the values of the function at a particular point of the interval AB, of course, which are called the node point, and the multiple, the constant multiple, right, I call the weights. All right, so that is our quadrature formula. Of course, there is an error term, and the quadrature formula has a degree of precision. So don't forget about the degree of precision of the quadrature formula. The degree of precision can be embedded in the error term. That is, if you know the error term, because the error term is written as a particular derivative of the function, right? And we know that the derivative in the error term is the degree of precision plus 1. That we know. And we tackled the trapezoidal rule, Simpson rules, because there are two Simpson rules, Boyle's rule. In fact, we did not even tackle Boyle's rule per se, but the formula is there. And now, from quadrature formula or quadrature rule, we define what we call Newton code. Newton code's rules are particular forms of the, it's a particular quadrature rule whereby the function that you integrate is just replaced by its polynomial interpolation, of course, plus the error term, right? So if you take the function, you replace it with this interpolating polynomial at the node point and integrate that expression, the formula that we obtain is called Newton code formula. We have open Newton code formula, closed Newton code formula. Open or closed depend on whether the endpoint, that is A and B, are part of the formula that is embedded in the formula. When you write your formula, do you have f of A, f of B? If they are included, those endpoints A and B, if they are included in the formula and it's a Newton code formula, you say that you have a closed Newton code formula. And the method that I listed here are all closed Newton code formula. If you look at the formula for the trapezoidal rule, you will see that f of A is there, f of B is also there. That's why you call f sub 0, f sub 1. We know that x0 is A, x1 is B, so they are there, they're embedded. So this is closed. Similarly, for the Simpson rules, for the Boyle's rule, they are all closed Newton formula. Now, in terms of the order of accuracy, right? The order of accuracy for for trapezoidal rule, is it trapezoidal? Yeah, is it trapezoidal rule? Anyway, okay, from there we move to composite, because we saw that with composite you can use the number of subinterval that you want. But if you just take the original Simpson rule or trapezoidal rule, the results are not that much accurate compared to the composite, because composite you decide to break each subinterval or interval into many subintervals in such a way that you obtain a required accuracy. So the advantage is one, it is the composite, because with composite you can play with the number of subintervals, whereas in the previous or the original formula, the number of subintervals is fixed. You don't play with that. They're given. What else from there? Then recursive trapezoidal rule. In the recursive trapezoidal rule, we saw that, of course, we still use the recursive. We still use our composite rule, but here the difference is that the number of subintervals is now a power of 2. It's a power of 2, and because we are using in the recursive formula, we are using a kind of extrapolation, because remember that the Richardson extrapolation technique that we use to define what we call the Rhombach algorithm. In that, each time we have the step size. We have, and by halving, we get a more accurate result. So in order to do that, we define the recursive, because with the inside the recursive, we embed the halving. They are already embedded, the halving. Because if you see in the formula with the recursion, let me share that particular window for the recursion. We will see that Tn minus or Tj minus 1 is half. So it embeds already the halving of the set of the step size. There we go. Okay, so this is what I'm talking about. So if you look at this expression, you can see that from this, because don't forget that b minus a here is h, right? Initially, when j is equal to 0, so if you come here, if you take this formula, when j is equal to 0, h is b minus a, right? And that's what we have here, b minus a. So this is h by 2. So this one, when we divide here by 2, it will take the h that is there, you will halve it. So each time, and this is already fixed here, so each time when you're performing this, you are halving h already into this formula, you are halving. Now the remaining here, this h, you'll be using this, so you'll be also halving each time. So that is why, if you look at the details here, when we take j equal to 0, j equal to 1, you can see that h is changing each time. Right. Because initially here, when j is equal to 0, b minus a is 4. So h is 4 here. Then after 4, you see that it's 2, is half. After 2 is 1, it has been half. After is 0.5, so it has been half, and so forth. So we are halving each time. And when we take this formula T0 divided by 2, we are also having the h that is into this expression. The h that appears here is also half. So it is half, wherever it appears is half. So this is our recursive formula. And we use that recursive formula and we use the recursive formula to define this, the Romberg algorithm, right? Okay, so today what we are going to do, we are going to tackle a new concept, and that is the concept of Gaussian quadrature formula. Now, you likely ask the question, but what is the difference between the Gaussian quadrature? Here we have Gaussian quadrature, and previously we talked about quadrature, quadrature formula, still quadrature formula. But they were mainly the Newton codes. Most of the formula we used previously were Newton codes formula. Most of them were Newton codes. Okay, now what is the difference now? The difference here, it is in terms of the degree of precision. Degree of precision, because remember that degree of precision indicates the degree of the polynomial for which the rule is exact. That is, if I take a polynomial of that degree, I integrate, the error term will be 0. So what I obtain with the formula is the exact, it's not an approximation. So as you will see, even from the statement here, if we have endpoint for the Gaussian quadrature rule, if we take an endpoint, that is the number of points. If there are endpoints, it means that we have n-1 sub-interval. Remember, the total number of points is the number of sub-interval plus 1, always. If I have 2 points, I have 1 sub-interval. If I have 3 sub-interval, I have 4 points. So the number of nodes, if you got a quadrature node, the node there, the quadrature node, the number of points that you have there, the node, we assume is n. There, n. Now, if it is n, the degree of precision will be 2n plus 1. Because the formula will be exact for polynomial will be less than or equal to. So this indicates what? The degree of precision of the method. Right? 2n plus 1. So that is it. So you see that it gives you a more accurate, we are accurate in terms of polynomial, right? Degree of precision. You see, it's 2n plus 1. So with the same number, if we go back to the previous one, so we saw that we can see here that the degree of precision is approximately twice the number of quadrature points or quadrature nodes, n 2n plus 1. Now, if I quickly scroll back towards the beginning, okay, so let's look at it. Look at the number of points here. If you just look for the Simpson 3/8 rule, okay, we also have the Bowles rule here. Okay, let us even start with the last one. N is equal to 5. That's the number. Oh, no. N here is the degree of precision. You see, the degree of precision is 5, right? Now, how many points do we evaluate? That is the number of points where we evaluate the number of node points or quadrature points. How many are there? 1, 2, 3, 4, 5. So we have 5 points, and we have also a degree of 5. Now, if we scroll up here for Simpson 3/8 rule, how many evaluation or how many quadrature points do we have? 1, 2, 3, 4. So we have more points, but the degree of precision is less than the number of points that we use to evaluate the integral. We evaluate at 1, 2, 3, 4 points, but the degree is even less. Yeah, Marley. The degree is even less, you can see. even less. Oh, that's terrible. That's horrible. Now, here, we count 1, 2, 3. Degree of precision, 3. Approximately equal. Back here, how many evaluation or how many points? 1, 2. How many, and what is the degree of precision? 1 is even less. Woo! Wow, wow. So I hope you understand now. On the other hand, if you use Gaussian, or yes, Gauss quadrature formula or the Gaussian quadrature formula, if I take n node point or quadrature point, the degree of precision is approximately the double. Whereas here, it's approximately the same, sometimes even less. I hope you appreciate it. I hope you understand where we are heading to. So we are heading towards something that is more powerful. Just with a few points, have higher precision. Just with a few points, have higher precision. Whereas here, to have a good precision, like 5, a degree of precision of 5, I need to evaluate at 5 points. If I use the bull rule, 1, 2, 3, 4, 5. So I need a lot of points to be able to reach degree of precision 5. I need 5 points, a lot, just for that. But with the quadrature formula, I need less than this to achieve this higher accuracy. When I talk about accuracy, yes, I mean the degree of precision. And what is it important? Because remember the numerical method, as I mentioned in the first semester, usually we approximate using what? Polynomial. We approximate function using polynomial. So if I approximate with a polynomial of a certain degree, that polynomial that I'm approximating with, that's what will give me the degree of precision. So that polynomial I'm using to approximate, its integral will be exact, right? I don't need too many points to get an exact representation of. I hope you get the message I'm trying to convey. So before I proceed, I want you to tell me if you understand that. Is that clear for everybody? The difference, because you need to understand what is the difference. Why do we need this contrary to the previous one? Because it's not good. We don't just proceed with new method for the sake of having new methods. That's something you need to bear in mind. If we bring it a new method, it's because there were flaws with previous method. We tried to solve a particular problem. That's why we introduced a new method. If you recall, even from numerical method 1, we started with Newton's when it comes to differential equation, to solve numerically a differential equation. We started with Newton's not Newton. Euler's Euler's method. Started with Euler's method. We saw that Euler's method was only first order accurate, which is not good when it comes to numerical method. Minimum of second degree or second order accurate is good, but Euler's is just first order accurate. You say it's not good. We need a better approximation. We move from there to improve Euler's method or the second degree Orango-Kutta method, and that is it. We introduce new method with more accuracy, right? So it's like that. A new method should come in to solve a problem, an existing problem. Is it clear, guys? If there's something you don't understand, please. This is the time for you to ask. Is everything clear in terms of why are we introducing the Gaussian quadrature formula. Is the explanation understood by everybody? Simeon? Simeon? Kashopi? Johannes? Class representative, say something. Your student, they don't want to say anything. At least you represent them. No. Are you also lost or what?
Yes, doctor.
Yes is for what?
Sorry, sir, I was in a noisy place. I had to move away.
Hmm? I'm listening to you, huh? Please talk. Say something. Because I don't want to be talking when the message is not going through. If you don't get the idea behind, I mean the motivation even, in the first place, before we proceed, it will be useless to proceed because I want to make sure that we are together before we proceed. Guys, I want you to say something. If you don't understand, say, I don't understand this, I don't understand that. And if it is clear, then indicate so that I can proceed, because I cannot proceed without any feedback on your part. Camelo.
Yes, doctor.
You are not saying anything.
Yes, doctor. No, I don't have any question.
It's not about having any question. I ask you if you understand the motivation behind the concept of the Gaussian quadrature formula. Why are we introducing the Gaussian quadrature formula? Do you understand that? Is there anybody who can repeat the motivation, who can tell us why the Gaussian quadrature formula is important at this stage before we proceed? I want to make sure that you understand. Can somebody, if nobody says something, I mean, the class representative should tell us what she understood. Is the class rep still with us? Okay, so this theorem gives us the methodology. Actually, it describes the method. The Gaussian quadrature theorem gives us actually the method to obtain this formula, which we call the Gaussian quadrature formula. So this is the formula. You can see it's a quadrature formula. It's a quadrature formula. It's that expression. But now the way we compute our W's and our Xi's are completely different, right? In the Newton codes or in the previous method, these points were chosen, right? You have your interval AB, then you decide to partition your interval the way you want, and then the next thing was to get interpolating polynomial, integrate it, and then you have your W's and the points are there. But here there's a different procedure. First of all, the point, you can see that the points are not chosen arbitrarily, right? The points, that is the quadrature nodes here, are selected to be roots of a particular polynomial Q here. Q is a polynomial, and you can see that the quadrature nodes here are roots, so they are not arbitrarily chosen. That's the first remark. And the polynomial Q is selected in such a way that the integral of Q and x to the k is 0 for k running from 0 to n. So meaning that I can write the general formula of Q as a polynomial of degree n plus 1. I can write that formula. And then if I have a degree of n plus 1, and it has n plus 1 root, and I impose that condition here, you see that k runs from 0 to 1. So there are how many conditions? N plus 1 condition. So I have a polynomial of degree n plus 1 with n plus 1 condition. So I impose that. I obtain a linear system that I can solve. Obviously, a polynomial of degree n plus 1 has how many coefficients? N plus 2 coefficients. But the number of equations that I have here is n plus 1. So the equation is a little bit of a determinant, a little bit. The difference is just 1. So which means that we have a possibility. I mean, it means that the polynomial here is not unique. It will be unique only by a factor, a constant multiple. That will be the difference. Okay, so if you look at this, it gives us already the methodology, right? The steps, how to determine the roots of Q. In fact, how to find Q first. To find Q, we impose this condition. And once U is obtained, we just compute the roots of Q. So once we have the roots, you can see how the weights are obtained. This is how the weights are obtained. So the weights are obtained by integrating the cardinal function. And this is exactly the same scenario in the Newton code. Because remember that with the Newton code, the weights are just the integral of the corresponding cardinal function. Okay, so that is it. So let us apply that to this particular example. Determine the Gaussian quadrature rule or formula with 3 Gaussian nodes and 3 weights for the integral. So this is our integral, f of x dx. We integrate from -1 to 1. Obviously, if you can integrate from -1 to 1, after you can replace this with ab, just through a change of variable. right? So we do that with negative 1, 1, but once this is obtained, we can define the same rule, but with an arbitrary interval AB. We will see that in the subsequent section. All right, so how many points do we have here? We have 3 Gaussian nodes, right? 3 Gaussian points or 3 Gaussian nodes. And we know that the degree of precision, if you look at this one, the degree of precision of Q is exactly the number of roots or the number of nodes. So here we say 3 nodes, right? If there are 3 nodes, it means that the degree of Q will be 3 also. So in that case, we write a general formula for a 3rd degree polynomial. You can see that this is a 3rd degree polynomial. So once you write this general expression for Q, we know from the Gaussian quadrature theorem that if we multiply Q by x to the k, where k runs from 0 to n, and we integrate from a to b, we set it to be 0. This will allow us to determine the coefficient, right? So that's exactly what we'll be doing here. So we have 1, 2, 3 conditions. First, second, third condition. Since the degree of this is 3, we also have 3 conditions there. 1, 2, 3. So k runs from 0, that is x to the 0 when k is 0, x to the 1 when k is 1, and x to the 2 when k is 2. So we have a total of 1, 2, 3 conditions. So we take this qx, we substitute there. You have 3 equations there. So we have a system of 3 equations, but how many are unknown? 4 unknown. 1, 2, 3, 4. So because of that, it means that there are many solutions, right? But we can still play around that. So by this imposition, we can choose. I advise you to do this for yourself to see all the details, all the steps involved. If we choose A0 equal to A2 equal to 0, it will reduce this. We are not choosing it arbitrarily. It is from this expression that we see that we can choose A0 and A2 to be 0. We are not choosing it arbitrarily. It's from this expression that we see that, okay, because there are many solutions, right? When there are many solutions, we can decide to fix some of the term and solve in terms of a variable or in terms of a parameter. So that's exactly what we are doing here. So, and that's what we get. So once we fix that to 0, qx is reduced to this expression. These two expressions. A1x, A3x cubed. Now, the second condition here, that is x to the 1 times qx equal to 0. So that integral will lead us to multiple solution, as we already said. Because you see that we have an expression that involves A1 and A3. Now, if you fix one, you get the other one, right? It's as if you remember in a curve, if you have something of this form, let's say you have an expression of the form ax equal to b. So you agree with me that if you fix this b, A depends on B. So if I fix B, this A will change. If I say, for instance, if B is 0, you see that A will be 0. If B is, oh, sorry, what did I say? If, okay, let me do this. Let's say I have this 2A equal to this. Now, if B is 0, you see that A is also 0. Now, if B is 1, A will be 1/2. So you see that A depends on B. If I fix one, I get the other one depending on the fixed value. So that's exactly what happens here. You have an expression of x1 in terms of x3, or x3 in terms of x1. So if we fix one, we get the other one. So that's exactly what we obtain when we integrate this expression. So you can do that. It's easy to see. Because if you integrate this, you can see that you get an equation in A2 and in A1 and A3, because the x will be integrated. That's exactly what happens here. Okay, let me do that for you. Right? Let me do that. So we integrating -1 1 x A1 x plus A3 x cubed dx equal to 0. So let me okay, so what I was saying, we are integrating from -1 to 1 x A1 x plus A3 x cubed dx. And that will impose to 0. So that implies from -1 to 1. So if we expand this, what do we get? We have A1x squared plus A3x to the 4th dx equal to 0, which implies, so if we integrate this, we have x. So we have A1x 4/4 plus A3 x 5/5 equal to 0. Now, you agree with me? You agree with me here that when we take this expression at 1, because we have at 1 and at -1. Right. Okay. So the first one we have A1, right? This one. And then if I take this, it will give me 0. All right. Are we together? What is this? What did I write? This is 2, huh? This is 2. Sorry, this is not 3. This is 2. So this will be 3. So this is 2. So we have 3 here and 3 there. Okay. So if I take that and this, so it will be double of this. So it will be 2. So this will be 2. This one will give us 2 into, so that will be 2 by 3, right? It will be 2 times this into A1 plus, similarly, this will be 2 times this. So it will be 2 by 5 into A3 equal to 0. So you can see that they depend on one another. Okay, because we have a common 2 here, we can simplify. We can cancel out by 2. So this will give us, so we have 2 here, 2 there, so we can factor by 2. So it will give us that this is equal to that. So we have A1 by 3, or I can write that A1 is equal to what? I take this on the other side. I can say 5A1 is equal to 3, -3. So this is -3 by 5 A3. So that's a relationship between the two. You can see that if I fix one of them, if I fix A3, I'll get A1. And if I fix A1, I will get A3. So they depend. They are dependent on each other. So this is the formula. So the formula that we obtain is A1 is -3/5 A3. Right? We can write one in terms of the other, or we can still say that okay, so that is it. So what were we trying to do? Let me look at the slide again. Okay, now we said if we take A1 to -3, if A1 is -3, what is A3? So if A1 is -3, you agree with me? If A1 is -3, you see, if I put -3 here, I will cancel out the -3 and I will multiply by 5. So this will imply that A3 is 5. So these are the values that we obtain in the note. So you see that this is our Q. So our Q X, since Qx is A1, x plus A3x cubed, right? I can substitute the value. So this will be -3x plus 5 x cubed So negative 3, 5, negative 3, 5. So this is what I obtain. So this will be the expression of our Q. Right? So that is the expression of Qx. Or you can also write that Qx is 5x3 minus 3x. You see? So that this is the expression. This is what we. All right, so that is it. Now from here, the next thing is just to compute the roots, right? So Qx equal to 0, what do we have? Okay, so we have Qx equal to 0. This is equivalent to, you can see that I can factor there by x. So I have x factor of 5, x squared minus 3 equal to 0. And this is equivalent to what? So here we have x equal to 0, or 5x squared minus 3 equal to 0. Right? So which is equivalent to x 0 or, now this one, x is equal to plus or minus 3 or square root of. So we have 1, 2, 3. So we have 3 roots. The degree of the polynomial is 3, and we have 3 roots. So already from this, we have the xi's, right? We have x0, or anyway, it depends. Okay, if you put that in order, we can take x0 to be the smallest, right? If we sort it and in an increasing order, so x0 will be negative square root of 3 by 5. X1 is 0. And finally, x2 is the reciprocal or the symmetry of this, which is square root of 3 by 5. Okay, so that is it. All right, so we have already the notes. What is left is what? Are the W's i's. The rest is how to find the Wi's. Obviously, we know the formula, right? Okay, you can integrate directly, or you can proceed otherwise. Use the fact that the rule is exact for a certain for a polynomial of a certain degree. Then you solve a system, you get the Wi's if you don't want to integrate. So you have two possibilities, right? Okay, so back to the notes, right? Let's go back to the notes. Okay, so we have the roots, they are there. So the remaining task is to get the W, the weights, right? Okay, so as I said, you can integrate directly using this formula, this one. You can do that, or you can proceed by the method of undetermined coefficient, this one. Okay, and that's what we will do because that's what is in the notes, right? That's what I chose to. So here, we use the fact that the rule, this rule that we have written will be exact for polynomial of degree less than or equal to 2. Of course, 2 is the, we took 2 because we need 1, 2, 3. In fact, it's more than that, right? It's more than that because if, because here, how many nodes do we have? 1, 2, 3. So it will be 5. The degree of precision of this is 5. So actually, it's for polynomial degree less than or equal to 5. But I don't need to write up to 5. No? There are many coefficients. But because we only need 1, 2, 3, we need 3 expressions. 3 expressions is for a polynomial of degree less than or equal to 2, right? Because for a polynomial of degree less than or equal to 2, you take k equal to 0, k equal to 1, k equal to 2. So you need 3 equations. I only need 3 equations for these 3 weights, right? Because there are 3 weights, it's enough for me to use a polynomial of degree less than or equal to 2 and impose this condition to say it's exact for this. I repeat, actually, the maximum degree here will be 5. 5. Because remember, let's come here. We say here that if k runs from 0 to n, the degree of precision will be 2n plus 1. All right. From 0 to n. Since we have 3 nodes, if we start from 0, it will be 0, 1, 2. So n is 2. Because we have n plus 1 node here. If you look carefully, here we have n plus 1 nodes. From 0 to n is n plus 1. So if we have 3, n will be 3 minus 1, which is 2. Now you multiply that n here by 2, you add 1. So 2 times 2 is 4 plus 1, 5. So this for when you have 3 nodes, the rule will be exact for polynomial degree less than or equal to 5. Right. But here we chose 2 only because we need to impose 3 conditions. So I repeat again, we say here polynomial less than or equal to 2, but it's actually 5. But we are using 2 because we want to impose 3 conditions. K is equal to 0, equal to 1, equal to 2. So it gives you a polynomial degree 2. But that is not the maximum degree. The maximum degree is 5, but we are using 2 because we want to impose only 3 conditions. I hope it is clear. Okay, so now if you take x to the k, for k equal to 0, it will be 1. For k equal to 1, it will be x, and for k equal to 2, it will be x squared. So we take this rule, we replace f of x with these 3 functions, 1, 2, 3. For the first function, when f of x equal to 1, we put 1 here. You can see that this is 1. We integrate this, we say it is equal equal, because we are saying it's exact, so it's equal. Now, if we put 1 here, it will be W0 times 1, which is W0, plus W1 times 1, which is this, plus W2 times 1, which is this. Now, if I integrate 1 from -1 to 1, it is 2. So this is my first equation. Now, if I take f of x equal to x, and I put there, you have x here. If I integrate x, the antiderivative is x squared by 2. From -1 to 1. So this is 0. So this integral is 0. Now I take f of x, which is x, this one, because k is 1. I substitute here and I say it's exact for that xk. Now, if I come here, I substitute negative square root of 3 by 3 here. F of negative square root of 3 by 3 is negative square root of 3 by 3. And that's what you have here. And you multiply it by W0. So that's what you have here. Plus W1 times f of 0. If I put 0 here, f of 0 is 0. So 0 will multiply W1. So W1 is not present. Now, if I take x equal to square root of 3 by 5, substitute there, it gives us square root of 3 by 5 times W2. That's what we have here. So this is our second equation. Now, the last equation is when we take f of x equal to x squared. F of x equal to x squared, which is here. I integrate this, the result will be that. And now I come to this, I substitute this. So if I square this and I multiply by W0, the square of this is 3 by 5. And that's what you have here. 3 by 5. Now, if I say x equal to 0, substitute here, it's still 0. 0 square is 0. It will multiply W1. So W1 is not present. Now I come here, I replace x with square root of 3 by 5. Substitute there is still 3 by 5. That I multiply by W2. So I have my 3 equations. So I have 3 equations, 3 unknown. So I solve this. So this is the system when you rearrange, right? If you rearrange this, it gives you the system. Right? You see that you can factor this by square root of 3 by 5. So if you factor, you get this. Right? You factor by or negative, start. And this last one you multiply or you factor by 3 by 5, then you get the sum equal to this. You cross multiply, multiply by 5 by 3. If you multiply this by 5 by 3, it will give you 10 by 9. Okay, so if you rearrange that, then you get this. So if you solve this equation, this system, these are all the W's that you obtain. So you have all the weights, so you can replace back into this formula. If you do that, this is the final formula that you will obtain. And this is what we call the 3-point Gaussian rule. This is a 3-point because we use 3 points. So we have just derived the 3-point Gaussian rule, which is this. Okay, I think we will stop here. We have exceeded by 3 minutes. Which is exactly the 3 minutes. We started 3 to 4 minutes late. It's not a way to justify that we exceeded. Yeah, I think we'll stop here. Is there any question before I stop?
So the release of test 1 results.
Tomorrow.
Okay. Thank you.
Okay. All the best. God bless you and see you tomorrow. Bye-bye.